Okay, so guys, let's continue from where we stopped last time. So, as a recall of what we did last time, we talked about two aspects of an NMR spectrum, how to interpret the spectrum. We talked about the position, the number of signals, okay, which is an indication of the different types of atoms present in the spectrum. Then we also talked about the positioning of the signal, meaning the chemical environment of the signal, which is represented by the chemical shift or the frequency. And that gives us information about the environment of the proton. So from the position of the signal, we can know if a proton is shielded or deshielded. And that gives us useful information about the molecule we are trying to identify. Then we also talked about the integration, the integral, which gives you information about the number of protons responsible for that signal, for that particular signal. That's what the integration is all about. And today we're moving forward. We're talking about another stuff that is important. We're talking about the splitting. Okay? So far we've been looking at NMR signal where you only have one peak. You know what I mean by one peak is, let's look at this NMR diagram here. If you look at this NMR signal, you only have one peak over here and you only have one peak over there. Usually we refer to those as singlet, meaning standing for single. So those peaks are singlet. Now, there are some NMR signal where a group of peaks actually appear to represent one signal. For example, over here, this is not one signal. When that is blown up, when we blow that up, let me show it clearly for you guys. You see, it may appear as one signal, but when you blow the spectrum up, you actually see that you have two signals in there. It actually shows you two signals. Okay? And if we look at the next signal, this is a group of signal over here, but when we blow the signal up, you can actually see four distinct peaks in there. Okay? So that's what we refer to as splitting. We refer to that as splitting. And the splitting is given by the formula n+1. The splitting pattern is given by the formula n+1. And n in the formula stands for the number of adjacent protons. Does that make sense? N stands for the number of adjacent protons. Yes, question.
You said what proton?
Adjacent.
Oh, okay.
Does that make sense? So let's try to interpret the spectrum we have next to us. Okay. Look at the chemical formula. CH3, CHCl2. Okay. Now, based on the formula, so far what we have done, we know that this will give us two signals because we have two distinct protons. Does that make sense? And so those are the two signals. That's information we know. And so let me label them, okay? I will call this guy A and then call this guy B. So this will be the signal due to proton A, and this other one will be the signal due to proton B. First one is A, simply because A is shielded. The closer you are to an electronegative group, the more deshielded you become. So that's how I know that the signal around 2 is A. Does that make sense? Then the signal around 6 will be B. Those are the two signals so far. Now in terms of integration, we have 3 protons responsible for signal A, and we have 1 proton responsible for signal B. That's what we've done so far. Now, the new step, what we're introducing today, is a splitting pattern. Why is signal A a doublet? We refer to this as a doublet. Why is signal A a doublet? And signal B, how many peaks are there? 4. So what name do you think we should give it? Maybe let's give it a quartet. Okay, let's call it a quartet. So baptize that a quartet. So why is signal A a doublet and signal B a quartet? Because when you look at signal A, when you look at the protons A, how many protons are adjacent to A? How many protons are adjacent, meaning next to A? 1. Okay, so the value of N will be 1. And so if we use the splitting formula N plus 1, that will give us 1 plus 1. And 1 plus 1 gives you 2. That's how we obtain that doublet. Does that make sense? Yes. When you have one peak, we refer to that as a singlet. When it is 2, we refer to that as a doublet. When it's 3, triplet. 4, quartet. 5, and so on and so forth. Does that make sense? Usually when you are more than 5, we simply say multiplet. Okay. But now, how do we have a doublet? Yes, Zakina, question. Remember we said N stands for the number of adjacent proton. Okay? Adjacent, meaning proton next to your proton of interest. So we are looking at signal A. We are looking at signal A. And we all agree that signal A is generated by the CH3 groups. Does that make sense? We all know that signal A is generated by this guy, CH3. So how many protons are adjacent to that CH3 group? That's the question. How many protons are adjacent to it? 1. Right? That is the only adjacent proton. We only have 1 adjacent proton, so the value of N is 1. So when you do 1 plus 1, you have 2. That's how come you have a doublet. Does that make sense? So if you look at signal B, let's look at signal B. Signal B is generated by this guy here, by that proton over there. How many protons are adjacent to signal B or to proton B? How many protons are adjacent to it? There are 3 protons. So the value of N is 3. Does that make sense? So there are 3 protons, so the value of N is 3. And so the splitting pattern will be 3 plus 1. And that gives you 4. That's why you have a quartet. 1, 2, 3, 4 signals. Yes. That again? This is signal B, and these are the 3 protons. Does that make sense? It will make sense, trust me. No, trust me, it will make sense. Let's look at this molecule. Let's look at this molecule. So this is another example, okay? This is another example. So, number of signals for this molecule, it will be 3. Everybody is okay with that, right? Because there are 3 different types of protons. There are 3 different types of protons. Now let's look at the multiplicity or the splitting pattern. We either refer to it as multiplicity or the splitting pattern. Let's look at the splitting pattern. Let's start with proton C. Let's start with the group of hydrogen C. How many hydrogens are neighboring C? How many? What I mean by neighboring, I'm talking about standing right next to C. Does that make sense? And in this case, what I mean by neighboring, you don't have to go more than 3 bonds away from C. You don't go more than 3 bonds away from C. Does that make sense? So let's do that again. This is C. So how many hydrogens are neighboring C? 0. Does that make sense? Yes, question.
I can understand how you would say 0, but at the same time, if you just go like 1, 2, 3, couldn't you say A and B or within 3 bonds? Within 3 bonds or something?
That's the extended structure, okay? What I've just drawn out there is the extended structure for what you have on the board there. And these are the groups of protons that we refer to as C. Does that make sense? Those are the group of protons we refer to as C. Remember, when I say neighboring proton, it means at least 3 bonds away from the group of protons C. And so if I want to count, this will give me 1 bond, 2 bond, and 3 bond. You notice that 3 bonds away, there's no hydrogen present in that area. Yes.
So when you say 3 bonds away, you have to start at that H.
Just like you saw me do it. Okay. Does that make sense? Let's do this. Maybe it will make more sense. Let's be real now, right? Yes. Now, let's see this. Look. Wow, it's still early in the morning. So, now, how many protons are responsible for signal C? You have 3 protons in C, right? There are 3 protons responsible for signal C. Meaning those 3 protons are chemically equivalent. Is that okay? They are all the same. So they are the same people. They are the same people. Okay? Now we are looking for neighboring protons. How many protons are neighboring C? Meaning standing next to the group of protons C. How many? That's the question. 0. Does that make sense? So 0. There's 0 protons standing next to C. And I told you that what I mean by neighboring, it means you need to be at least 3 bonds away from any of the C's proton. You need to be at least 3 bonds away from any of the C proton. And in this case, we have 0. Does that make sense? So we have 0. The value of N for C will be 0. And so the splitting for C will be 0 plus 1. That gives you 1. So C will be a singlet. Does that make sense? C will be a singlet. It means that if you go to the NMR spectrum, you will only see the signal responsible generated by C as just a single line. That's the meaning of being a singlet. Yes, Shelby. Should I remove my t-shirt also? Probably I will also have to remove my t-shirt. Okay, let's start this thing all over. We've talked about integration already, right? That's fine. Integration gives you information about the number of protons that generates the signal. Okay? Number of protons that generates the signal. We've talked about the chemical shift. That gives you information about the chemical environment where the proton is found. Now we're talking about something else. We call it the splitting pattern or the multiplicity. Okay? Because NMR signal is not just a single line. You will have signals that will be made up of 2, 3, or 4 lines or 5 lines. Those different lines, we refer to them as a splitting pattern. Okay? Let's go back to this first spectrum here. Let me do some home care work here and clean this thing up. Okay, over here we have an NMR spectrum of CH3CHCl2. So that's the molecule, that's the spectrum. We need to be able to match the spectrum. Okay? We know we have 2 types of hydrogen in that molecule. 2 types of hydrogen. And we'll label them. So we have a group of hydrogen called hydrogen A. And we have another group of hydrogen called hydrogen B. Does that make sense? Now, because hydrogen B is next to chlorine, meaning standing next to chlorine, it means that the hydrogen B are deshielded. If they are deshielded, they will have a high chemical shape. And so I know that this signal here is responsible by proton B. And over here, the signal will be responsible by proton A. Does that make sense? Now, in terms of integration, the integration for signal A will be 3. That's an indication that we have 3 hydrogens responsible for signal A. Is that okay? And the integration for signal B will be 1, indicating that we only have 1 hydrogen responsible for signal B. Are we good up to this point? Okay. Now, the next thing I will do, I will expand the structure. Let's expand the structure. That's the expanded structure over there. Okay. Now all the blue protons belong to A. They are all the blue protons belong to A, and the red one belong to B. So if we look at B, okay, how many protons are neighboring B? How many protons are neighboring B? B is the red protons. And remember, when I mean by neighboring, means 3 bonds away from B. And so this is B over here. That's B over there. So I will look 3 bonds away from B. This is the first bond, second bond, and the third bond. Okay, I see a hydrogen. First bond, second bond, and then third bond. I see another hydrogen. First bond, second bond, and third bond. I see another hydrogen. If I go this way, that will be 1 bond, and that's it. There's no hydrogen in that direction. Does that make sense? I go down this way, there's no hydrogen in that direction. Question.
Why do you count the hydrogen as attached to B?
Say that again.
Why do you count the hydrogen attached to B?
Because that's our hydrogen of interest. B is the hydrogen of interest. We are looking for how many hydrogen are neighboring B. Does that make sense? How many hydrogens are neighboring B? And so in this case, we have 3 hydrogens neighboring B. Does that make sense? So the value of N is 3. And when you do the formula N plus 1, that gives you 4. That's why you will have 4 signal for B. Does that make sense? Yes.
So the 1 in the N plus 1 represents the hydrogen on
adjacent carbon. That's what I said. Okay. On adjacent carbon. So you do the same thing with a group of protons of A. How many hydrogens, how many protons are surrounding A? How many? No. 1. How many protons are adjacent to A? Yeah, surrounding A, neighboring A. We only have 1 proton. Does that make sense? We only have 1 proton, and it's this guy, proton B. And so the value of N is 1. So 1 plus 1, 2. That's how you have a doublet. Still not? We'll move forward. And so we can use the same ideology to determine the splitting pattern over here. So like I said, let's look at the group of protons in C. How many protons are neighboring C or adjacent to C? In this case, there will be 0. And so the value of N is 0. 0 plus 1 is 1. And when you have 1, we refer to that as a singlet. Does that make sense? If you look at B, how many protons are adjacent to B? How many protons are adjacent to B? 3 protons are adjacent to B. So the value of N is 3. 3 plus 1 gives you 4. So B will generate 4 peaks in the signal. Splitting pattern will be 4. That's why we refer to it as a quartet. Now if we look at a group of protons in A, how many protons are adjacent to A? There will be 2 protons adjacent to A. So 2 plus 1 gives you 3. Does that make sense? 2 plus 1 gives you 3, and we have a triplet. Does that make sense, guys? And now I hope you can now understand the splitting pattern in this other molecule here. Yes?
At what point, like looking at B, you said multiply? Because earlier you said quartet and then.
Remember I said when you usually 5 and above, sometimes people will call 5 as a quintet, 6 as a sextet, but if you are not able to identify them, you just go 5 and above, you are free to also call it a multiplet.
You'll accept either or.
Either or. Okay. So same thing here. Let's look at B. In this case, it's very interesting to understand B. How many protons are neighboring B? There are 5. Does that make sense? You will have 3 on the left side and 2 on the right side. Well, right in respect to the way I look at it. Does that make sense? So you will have these 3 protons here and these 2 protons here. So B will have a total of 5 neighbors. So 5 plus 1 gives you 6. So actually B should be a sextet. Okay? A sextet, or we simply refer to it as a multiplet. Usually when it's more than 5, we just go with multiplet. If you call it a sextet, that's fine. If you call it a multiplet, that's fine. Is that okay? Yes, sir. That says what? There's a problem, and yes, I will correct it right now. Thank you. So look at a problem here. There's a problem with the note, okay? Correct your note. Look at D. Do you see the problem? So what should D be? What should proton D be? What should the signal of D be? The note says a triplet. Do you agree with the note? I don't agree with the note. Huh? It will be a singlet. Zico. Yes, sir. Huh? Oh, I drew it wrongly?
I was about to say the adjacent carbon.
No. Let me try to figure it out. Hold on. 1, 2. No, that is correct. It's supposed to be a triplet.
Yeah, I was about to say because the adjacent.
No, it will be a triplet. Because I didn't take a look at it. Thank you, sir. It's a triplet, guys. It's a triplet. It's 3 bonds away. It's 3 bonds away. It's 3 bonds away. Oh, by the way, there's something I need to mention here again, okay? Now, let's look at this structure. There's another word I want to introduce here. So B is standing next to A, right? And A is standing next to B. Because if I stand next to you, it means you're standing next to me. Okay? It's reciprocal. So A and B are said to couple. That's the way the term we use. You say B is coupled to A and A is coupled to B. And if 2 proton couples each other, then they will split each other. Does that make sense? So we'll technically say B is coupled to A or A is coupled to B, meaning they're standing adjacent to each other. Now, in the proton NMR, equivalent protons do not split each other. Okay? Equivalent protons do not split each other. So if we look at the structure of bromomethane, we'll only have a singlet. The signal in the NMR spectrum for this will only be a singlet. Although we have 3 hydrogens, it's because all those 3 hydrogens are equivalent. And so if they're equivalent, they cannot split each other. It means they have 0 adjacent hydrogen. Does that make sense? If you also look at the structure of 1,2-dichloroethane, these 2 groups of protons are exactly the same. They have the same chemical equivalence, same chemical environment. And because they are chemically equivalent, they will not split each other. The NMR spectrum for those protons will only be a singlet. Does that make sense? Is that okay, guys? Because these protons are exactly the same. This guy is exactly the same as that guy. And so they have no neighbors. So that will give you only a singlet. That's what we mean by equivalent protons do not couple with each other. What causes a splitting? Why is it that the protons split each other? Why is it that the protons split each other? So to explain this, we'll use a simple example, a doublet. This is a doublet. How do we generate a doublet in the NMR spectrum? We can only generate a doublet when you have 1 adjacent proton. That's the first thing you need to understand, right? A doublet can only exist if you have 1 adjacent proton. If you have 1 adjacent proton. So in this case, we are putting together 2 types of nuclei. Remember, NMR has to do with the nuclei, the spin of the nuclei. Okay? And so, signal 3, here, let's use only one of the protons in signal 3. And we have only 1 adjacent hydrogen to signal 3. Okay? So we are looking at 2 types of nuclei over here. We're looking at 2 types of nuclei over here. And so, when you apply the magnetic field with those 2 types of nuclei, one of them could be aligned. Let me take it back clearly. When you look at a signal from the proton, from the CH3 protons, all of those protons, they will have their spin, okay? And that spin can align with the magnetic field. And because it's having only 1 neighbor, that neighbor will be able to split that signal into 2. It will split the signal into 2. One of the signal will be at high energy and the other signal will be at low energy. That's what we call the splitting. So this proton will split the signal generated by a CH3. And that will split it. One will be high energy, the other one will be low energy. And the splitting, it uses all possible combination in order to split them. And so when you only have 1 signal, the only combination is split that into 2. One will be the alpha, the other one will be beta. And so that's how we have a doublet. That's how a doublet is being generated. Is that okay? I will use the same ideology in order to generate other type of signal. If we want to generate, what is it? The next one will be a quartet. We want to generate a quartet. Okay? In this quartet, the major signal, the major chemical shift will be that of the methane proton. If there were no proton, if the methane, imagine the methane had no signal around it, it will only give you 1 peak. But because it's having 3 neighbors, each of those 3 neighbors will split the signal. Does that make sense? Each of those neighbors will split the signal. And so they will split that signal into 4. Because there are 3 of them. They split the signal into 4. And that's how come we have a quartet. Is that okay? That's just been trying to explain the mechanism behind splitting. Each of those will split that signal into 4, and that gives us a quartet. Okay, and usually if you look at the quartet, the way the quartet is drawn, the middle signals usually have a tall peak, and the outer signal will have a short peak. And if you look critically, they kind of follow a ratio of 1:3:3:1. Does that make sense? So the peaks don't have the same height, as opposed to the doublet. In the doublet, they have exactly the same height. So in the doublet, the ratio is 1:1. The height of the signal is a 1:1. But over here, the height of the signal is 1:3. Does that make sense? Okay. Let's not bother about that. That will bring more complication to our life. Yeah, but it will bring more complication to our life. Just like what I told you before, guys, you can only observe splitting if the adjacent protons are about 3 bonds away from you. That's only when you can observe splitting. If you are more than 3 bonds away, you will not be able, more than 3 single bonds away, you will not be able to observe splitting. Okay? You can only observe splitting if you are 3 bonds away. So, A and B will couple each other because they are exactly 3 bonds away from each other. So, you will be able to observe the splitting there. In this case here, A and B will not be able to split each other because they are more than 3 bonds away from each other. Does that make sense? We're looking at 2 cases here. In the first case, proton A and proton B are exactly 3 bonds away from each other. 1, 2, 3. So they will split each other. In the second case, proton A and B are 4 single bonds away from each other. So they will not split each other. Does that make sense? Now in the third case, remember I said single bonds. In the third case, proton A and B are 4 bonds away, but one of those bonds is a double bond. Exception to the rule, right? One of those bonds is a double bond. So A and B will split each other. This we usually refer to that as long range. We refer to that as long range splitting. So when you have a double bond, you can actually extend the splitting by an extra bond. That's called a long range splitting. Say that again. Yes, I can explain why. Look at that structure. If you look at that structure, yes, okay, the presence of this double bond here makes A and B closer together in space. Do you see that? So it brings them close to each other. That's what the double bond does. Whereas when you only have single bond, A and B are far from each other. Does that make sense? So that space close to each other, that's why they are able to split each other. Remember, splitting has to do with you being a neighbor, how close you are to me. And so the double bond makes you get closer to me. Does that make sense? Splitting has to do with how close you are to me, and the double bond makes you closer to me. Yes.
Okay, so like the double bond, so that's kind of like a cis-trans thing. So
yes.
Would it sometimes do it, or would it all the time do it? Because if it's cis was on the same side, then I could see it. But if it's on opposite sides, it won't. I don't think it'll show the signal.
Okay, it will always do that, but the efficiency will not be the same. Did you understand his question? When you have a double bond, you can form a cis-trans. When you form the cis, like in this case, they get close to each other. But if you have the trans, they will be far away from each other. And he's asking me if we'll still be able to see splitting if we have the trans. The answer is yes. But the strength of the splitting will not be the same. The guys that are cis will have a stronger splitting compared to those other guys that are trans. Does that make sense? And because he mentioned that, it now brings in the concept of what I call the splitting constant. What is that? Are we there yet? We'll get to it. We'll talk about the splitting constant very soon. What the splitting constant is. So it's just a number that we use to identify how strong or how weak the splitting can be. Okay. Any questions so far with the splitting? All I need from you guys to remember is the formula n+1, okay, where n stands for the number of adjacent hydrogen. And I want you guys to be able to tell me, why do we have a quartet, why do we have a triplet? If we see a signal that gives me a triplet, then I know that that signal is neighboring 2 other hydrogen. Does that make sense? If I see a signal that is a quartet, then that signal is neighboring 3 other hydrogen. And those 3 hydrogen, you can have 2 on one side and 1 on the other side. Or you can have all 3 on one side and 0 on the other side. Does that make sense? That's all I want you guys to take note. That's all I want from you. If I have a singlet, it means I have 0 neighboring hydrogen. Does that make sense? So let's look at the NMR spectrum of 1,3-dibromopropane. NMR signal of 1,3-dibromopropane. So by looking at the structure of 1,3-dibromopropane, we can only have 2 types of signal. We can only have 2 signals over there. And the signals are labeled A and B. The signal B are chemically equivalent. Okay, they have the same chemical environment. Because B is next to bromine, the proton B will be deshielded. Okay, and so over here we'll have a signal responsible by B, and over here we have a signal responsible by A. Does that make sense? In terms of multiplicity, in terms of integration, the integral follows a ratio of 1:2. So remember, I told you last time that integration can be the direct number of protons, or it can be a ratio. Does that make sense? And so here the integral was given as a ratio, 1:2. So you have 2 times as many protons in B than there are in A. Does that make sense? So in terms of multiplicity, that's where we're interested now. In terms of multiplicity, if we look at signal A, the protons in A, they have 4 neighboring hydrogens, 2 on each side. Does that make sense? They have 4 neighboring hydrogens, 2 on each side. So we expect A to have 5 peaks, a quintet. Does that make sense? So we expect A to be a quintet. And that's why we have a quintet over there. Now B, how many protons are neighboring B? 2. Does that make sense? You only have 2 protons neighboring B. And so we expect now B to be a triplet. Does that make sense? Same story over here. We are getting more complex. The same story with this other structure. Whenever you're given a structure, the first thing you want to do with the structure is identify each signal. How many signals will you have in the structure? It turned out that with this structure, you will have up to 5 signals. A, B, C, D, E, and F. Oh, sorry. A, B, C, D, B, E, or whatsoever. I don't know even the alphabet. Whatsoever. So you have 5 signals. The first thing I want you guys to understand, do you all understand why we have 5 signals over here? Signal B are chemically equivalent. Signal B are chemically equivalent. Okay? Those 2 methyl groups are the same. That's why we call them B. Now, the way the alphabet, the way they are lettered, is with respect to their chemical environment. The more shielded protons are labeled A, and the less shielded or the more deshielded are labeled E. Does that make sense? So A is more shielded than B, which is more shielded than D, more shielded than C, or whatsoever. Does that make sense? So the more shielded will be A, and the less shielded will be E. That's the way it has been labeled. Now, without looking at the NMR spectrum, I want us to determine the multiplicity without looking at the NMR spectrum. So if we focus on proton A, what will be the multiplicity of A? I need that from you guys. What is the multiplicity of A? Tyler? Any other one? What's the multiplicity? Kaira? What is it? Triplet. How many protons are neighboring A? 2. And so the value of n is 2. 2 plus 1 gives you 3, right? So A will give us a triplet. Now C. What will be the multiplicity of C? There are 5 protons. Okay? So the value of n is 5. 5 plus 1 gives you 6. So you have a sextet. Okay? So you sometimes call it a sextet, or you can just say it's a multiplet. It depends on you. Is that okay? D. How many protons are neighboring D? Only 2 protons are neighboring D. So D, you expect D to be a triplet. Does that make sense? What about E? How many protons are neighboring E? Can everyone see the 6 protons? Okay. E will have a total of 6 protons neighboring E. So what will be the multiplicity of E? It will be a multiplet. Is that okay? So E will be a multiplet. B, how many protons are neighboring B? 1. Does that make sense? We only have 1 proton neighboring B. So B will give us a doublet. Does that make sense? Because n equals 1. You have 1 plus 1, 2. So that gives us a doublet. Are we good up to this point, guys? Yes.
So for E, you say that it's a multiplet with this 2 that but since they're trying to be the same, why would they count like
When you count them differently, although they are chemically equivalent. Okay, so that's why E will have 6 neighbors. And so we give us 6 plus 1 peak. Does that make sense? Are we good, guys? So if you now turn around and look at the NMR spectrum, you will have it exactly there. So you can now guess. This is a doublet here. And so that doublet would most likely be from B. Does that make sense? That doublet is most likely from B. Now, we have a triplet over here. This is a triplet. Let me zoom it so you can see. Do you see the triplet? Okay. We have a triplet over here. Now, if I go back to the structure, there are 2 protons that can generate a triplet. You have proton A and proton D. Which one do you think is responsible for that first triplet? Is that okay with everyone? Because A is shielded. Does that make sense? So this will be A. Now, you guys cannot see very well. I will see it for you. This other one here. Let's go to this other triplet. I will skip this one for now. So this other triplet here will definitely be for D. Does that make sense? We have a triplet over here. And so the only guy that can give us a triplet is D. Is that okay? So this will be D over here. Now, over here, let me zoom it so we can count the number of signals. Oops, too much. God. So how many signals do we have there? 1, 2, 3, 4, 5, 6. Okay, so that's a sextet. Is that okay? We have a sextet there and we know the structure. Which one gives us a sextet? C. So that would be proton C over there. Does that make sense? And of course, then this one will be E. So if you count the number of peaks there, it will most likely be 7. And so this is it here. It has been blown up. You have it here. 1, 2, 3, 4, 5, 6, 7. So that's why that guy gives you 7 bits. E. Does that make sense, guys? So here we are able to match a spectrum to a structure. Okay, here we are able to match a spectrum to a structure. Now, from now, I will also be able to expect you guys, if I give you a structure, you should be able to like predict what the structure of the spectrum will look like. And the most important, if I give you a spectrum, you should be able to tell me what the structure is. Yes?
So, if we don't have the spectrum, I don't know how, I don't understand how B is more shielded than C. Like, how do you differentiate?
How B is more shielded than C? Remember, B is connected to a carbonyl group, right? B is connected to a carbonyl group. Carbonyl group is electron. What is B? Oh, B, and you're comparing what B and C? Oh, okay. B is a CH3 and C is a CH2. Remember, we talked about it in class last time. If I have to go back to the note. Methyl, methine, and methane protons, or methylene, and methine protons, those 3 types of protons, primary, secondary, and tertiary protons. We said the primary protons are usually shielded, then the secondary protons, and then the tertiary protons. Does that make sense? So, B is a primary proton, and C is a secondary proton. What I mean by secondary means it's on the secondary carbon. What I mean by primary means it's on the primary carbon. So primary protons are usually more shielded than secondary. Does that make sense? Yes.
Okay, so
A is primary too, yes.
So how to calculate the chemistry?
Now A is primary too, but you notice that B are kind of much more closer to oxygen than A is. Does that make sense? And so the fact that the B's are a little bit closer to oxygen than A is, the B are a little bit shielded than the A. Does that make sense?
Yeah.
Is that okay? Because remember, the shielding has to do with your distance from an electronegative group. Let me see if I can get something from the textbook before we move forward. So let's look at number 54 from your textbook, guys. Let's look at question 54 from the textbook. I don't know if you guys will have it in front of you. It says we have the proton NMR spectrums of 3 isomers. Proton NMR spectrums of 3 isomers with molecular formula C4H9Br. Which isomer produces which spectrum? So we have 3 spectrums. We have 3 spectrums for 3 isomers. And so we need to match them. Which isomer produces which spectrum? So we are looking at the isomers of C4H9Br. The first thing we have to do is to draw the structure of all the 3 isomers. Does that make sense? First thing we have to do is come up with a structure of all the 3 isomers. So the first structure, what comes to mind directly will be CH3, CH2, 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 Br. Okay, that will be one of the structures for the isomer. We'll just draw the structure of the isomer, then we'll match the structures to the spectrum. Does that make sense? So that will be the first isomer. What about the second isomer? Second isomer, we'll just keep moving the Br, okay? We'll move the Br around. So we can have CH3, CH2, CHBr, and CH3. That's a possible structure. What about the third structure? What should the third structure be like, guys? I'm looking if I have a different ink here. The third structure. What is it about the third structure, guys? Let's see. I mean, the third. That will be the third structure, right? Oops. Yes. That's the third structure. Does that make sense? So those are the three isomers. The blue, the green, and the red. Those are the three isomers of C4H9Br. Now we have to match each spectrum with those ones. Okay? And we can start following the logic that we know. If we look at structure B, how many signals do you expect to see in structure B? How many signals will structure B give you? The spectrum of structure B. Remember, the signal tells you the number of different types of hydrogens you have in there. So, how many different types of hydrogens do we have there? Oh, 9 o'clock. 4, right? Guys, please, I want us to be more active. I know it's early in the morning. So how many different types of protons do we have in a blue structure? 4. So we expect the blue structure to give us 4 signals. What about the red structure? How many signals? 4. Okay? And the green structure will give us 3 signals. Is that okay? With the green structure, we only have 3 signals. So by virtue of the number of signals, we can already distinguish. Does that make sense? So, let's have all the 3 spectrums. Over here I have 1, 2, 3, 4 signals. Over here I have 1, 2, 3, 4 signals. And down here I have 1, 2, 3 signals. So the guy with 3 signals will correspond to the green one. Okay? So this is the third spectrum. Does that make sense? Only by virtue of the number of signals. That's the third spectrum. And then you can still determine the multiplicity. You can still do that. You can still determine the multiplicity. Okay? If you look at the multiplicity, this proton here should give you a doublet. And so if I go down there, if I look at the signal, you see we have a doublet there. Does that make sense? Yeah. And we also have a multiplet over here. You can guess the one that will give you the multiplet. Let me draw out the structure here so we can see. That's the structure. I want us to understand the multiplicity. That's the structure over here. Okay? This will give us a doublet. This gives us a multiplet. Is that okay with everyone? What about the methyl group? What kind of multiplicity are we going to have for the methyl group? Doublet. Is that okay? The methyl group here will give a doublet because we only have 1 level. This gives a multiplet because we have 6 levels. Does that make sense? And this gives a doublet because we only have 1 level. And now you can match it up if you want to. So the multiplet goes here. We have 2 doublets. One of them is next to bromine. So the one next to bromine will most likely be this one. And the one away from bromine will most likely be that one. Does that make sense? Now we need to separate the next one. We have 2 structures remaining. The blue and the red. Those colors, sometimes I mix them up. The blue and the red. Let's give the multiplicity, please. Multiplicity for these hydrogens here. What is the multiplicity for that one? So that is a doublet. Multiplicity for this guy. So that will be a sextet, right? So I will call that M, multiplet. The multiplicity for this guy over here. Well, that will be what? How many levels are there? Yeah, it will be 5 peaks, right? It will be 5 peaks. Okay. So 5 peaks, let's call it quintet. So we don't mess up. Let's call that a quintet. Is that okay? Or no, let's call it quintet with capital Q. Lowercase q, I use that for quartet. And the last one, what would be the multiplicity? Triplet. So that would be a T. So let's do the same game with the blue one. Over here, the first one, what is the multiplicity? Multiplicity here. Multiplicity here. Sextet, multiplet, okay. And over here, what's the multiplicity? So do you see that based on the multiplicities, we can distinguish the spectrum? Based only on the multiplicity, we can distinguish between the blue and the red. Does that make sense? Now, down here, what do we have? Oh, this thing is not very clear. It looks clear in front of me, but it looks clear in front of me here. So the signal, this signal here around 1, this is it here, the blown up signal, okay? The signal around 1, this one here, this is it here, that has been blown up. So it's a triplet. Is that okay? So that's a triplet. Now the signal around this other signal here, this guy here, this is it here. It has been blown out there. Do you see that? So that's a doublet. Now very close to it, next to it, there's another set of signal here. Very close to it, there's another set of signal over here. Okay? What is that? A quartet. Is that a quartet or a quintet? That's... No, it's 5, right? It's 5. That's a quintet. And over here, I will guess it will most likely be a multiplet. Is that okay? And over here, it will be a multiplet. Does that make sense, guys? Nice. Nobody is with me today. So the first spectrum corresponds to the blue structure. Oh, sorry, the red structure. Is it red, right? Yes. The first spectrum corresponds to the red structure. Is that okay? The first spectrum corresponds to the red structure. And I would definitely guess that this one will correspond to the blue. But you have to convince yourself. You have to convince yourself that this is a triplet and that this is a triplet. Is that okay? This is a triplet and this is a triplet. Over here, these things are really hard to see. This is a quintet. This is a quintet and this is a multiplet. Is that okay, guys? So that's a quintet and that's a multiplet. So you can use multiplicity to distinguish those spectra. Or you can also use integrals. You can use the integral numbers to distinguish between the spectrums also. Does that make sense? Should we continue? Yes. Yes, we'll only continue. I will not teach anything more. We'll only answer questions now. Yes. Say that again. The course ID? Oh. That's the course ID for the homework. I'm looking for more questions. I'll just go straight on the section. Let's look at this problem. Problem number 25. Let's look at problem number 25. Yes. 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 Let's look at problem number 25, guys. Let's answer number 25 together. Please, please. Let's do that. Number 25. How can the proton NMR spectra distinguish between the following compounds? A, B, and C. Follow up. How can the NMR distinguish between A, B, and C? Okay.
It has to do with the fact that the bromines are different, like proximity to the night.
Multiplicity. So let's try to distinguish. How would the NMR, the proton NMR for this guy be distinguished? Let's look at A, for example. Okay. So how many signals do you expect to see on the NMR of A? Meaning, how many different types of protons do you have in A? So you expect to see 4 signals in A. Does that make sense? You expect to see 4 signals. There's a hydrogen here, different from this one, different from that one, different from that one. So for proton NMR A, we expect to see 4 signals. Is that okay? What about B? How many signals do we expect to see for B? A signal there, right? For that proton. A signal for this guy. A signal for this guy. And a signal for that guy. So for B, we also expect to see 4 signals. Does that make sense? What about C? How many signals do we expect to see for C? We expect to see 2 signals for C. These and these are the same. They will give us the same signal. Then this one and this one gives us the same signal. So we'll have 2 signals for C. Now, let's look at the multiplicity. Let's look at the multiplicity. Let's start with A. So I will number those protons 1 up to 4, okay? Let's call this proton 1, proton 2, proton 3, proton 4. Does that make sense? So for proton 1, what will be the multiplicity for proton 1? It will be a doublet. Does that make sense? This is proton 1. The only neighbor we have is 2. Does that make sense? Galena, does that make sense? I knew you would say that. I knew you would say that. Yes, I knew you would say that. I knew she would say there's a double bond there. So what would a double bond do? It might expand it up to 4 bonds. That's called long-range coupling. That's called long-range coupling. So technically, it will be a doublet if your instrument is weak. If the instrument is strong, yes. Okay, let's stop it with the doublet for now. Let's take it as a doublet, please. Let's make life easy. Let's make life easy, okay? So we expect this will be a kind of doublet. We expect this will be a kind of doublet. Is that okay? What about 2? We expect this to be a triplet. We expect this to be a triplet. We expect that to be a doublet. Does that make sense? Is that okay? What about number B? In B, this would be a singlet. Is that okay? Because there's no neighbor. And over here we have a doublet, a triplet, and a doublet. Does that make sense? Then what about C? C, this would be a doublet, and that would be a doublet. Does that make sense? Just based on those, you should be able to distinguish the NMR of those three compounds. Does that make sense? But now, one thing I want to tell you guys is that all of them are hydrogens on the benzene ring. They are all hydrogens on the benzene ring. And according to our table, hydrogens of the benzene ring appears between 6.5 and 8. That's the region on the NMR spectrum where they appear. And so because that region is very narrow, sometimes it's hard to see all those singlet, those doublet, and those triplet. They might just kind of jam up together, okay? They might all appear together. Look, for example, like this. You might end up having something like that. Does that make sense? Because this is a region between 6.5 and 8. When I see a signal in the region between 6.5 and 8, then I know there's a benzene ring. But how is the benzene ring substituted? It depends on the pattern. But when I look at this pattern, it's kind of hard for me to see all those double, those triple, those single. Does that make sense? But then, when you have a benzene ring, you can see again, look, the region between 6.5 and 8. You see what happens there. So when I see that, I know I have a benzene ring.
Like what we said about that first one that you showed us, putting all that in close.
This one here is hard. Unless we actually blow it out and make it clearer for you guys, you'll be able to see exactly the kind of patterns that will distinguish here. Does that make sense? If we blow it out, if we give you a real case situation, you'll be able to actually see it clearly. Are we good? So we've basically done 90% of proton NMR. Basically. What is remaining is more of, some little technical issue that's remaining. So you guys, I expect you guys to be able to look at the proton NMR and at least be able to guess what the structure will be. So your textbook, your homework is not well furnished, but your textbook is well furnished. Please look at your textbook and start solving. I'm sitting in my office and my door is open. If you understand NMR, it becomes the easiest thing on earth because it's just a puzzle. But if you don't understand it, it will be like a nightmare. It will be like a nightmare.
Hi, friend.
How you doing?
Good. I have a question. Okay, so you know how you do labeling A, B, C in the family, right? Wait, okay, so do it again. You do family. Label
the A, B, C, and then the A being the more shielded and B.
Okay, so like for some examples you have like 2 A's.
Because they have the same environment. It means those protons are the same.
So like this.
No. Yes, okay, yes. Like this one. Like this one. They are the same proton. Look, this hydrogen here is next to a bromine and next to a hydrogen. And this hydrogen here is also next to a bromine and also next to a hydrogen. So you see the environments are the same. That's why they're the same. It's the same reason with these ones here. Yes.
Do you know the time for our
Friday 6:30.
Oh, you changed it to Thursday.
No, it wasn't changed. It was maintained.
So it's going to be Friday the 24th at 6:30.
I think Friday the 31st. I think it's January the 31st.
Because on the homework is due the 24th.
We'll adjust it. I will check the syllabus, but I think it should be on the 31st. Okay, I think it should be on the 31st. I will check that. If I don't talk about it, remind me, please.
I sent you an email, but I didn't get a response about like if you would be able to write me a letter of recommendation.
Oh yes. When do you need that?
Like beginning of February, but I'm gonna come to your office. Thank you.
Hey, Martin, how you doing? Anytime you see me.
And you have any services in your office?
Yes.
So
So yeah, you can carry on and pick it up.
if you had any hard copies,
Yes, you can come to my office and get a copy.
Okay.
Yes.
So, I have lab at 6 to 9:50 tonight, Tuesdays and Thursdays. But there's only, and I have class tomorrow. No, I have class yesterday on Wednesdays from 4. Oh yeah, from 3 to 4:50. Okay, so Sierra only does her tutorings on Wednesdays from 4 to 5:30, and I also have something right after that class. So I won't even be able to attend. Even if I did, it will only be for 30 minutes. And then for today, I can't attend because I have lab. So I was wondering, would you be able to override me into your lab on Tuesdays and Thursdays from 2 to 5? No.
I have 28 students in that lab already. I have 28 students. Seniors, ladies and possible. How are you going?
I'm good.
How's your break? How was the class?
It's good so far.
Yeah. Are you in my lab?
No, I don't.
I'll go with Dr. Wadena. Okay. Oh, you had a lab yesterday? Yeah, just introduction.
So about this project, I'm a little confused.
No, it's easy. Don't worry about that.
See,
Yeah. Trust me, it's easy. Don't worry about it. It's model, right?
see, I think our points, I don't put the date on it.
Then put the date on.
You already know her, so just do what she does. Yeah. Yeah. I have 28 students. I will really love. Another person will come and tell me you can be number 30. Yeah.
What happened to get 28?
Huh?
You overrided 20.
Because he came crying like he did, and then the person told me I will only be the number 26. I was like, okay, yes. I will only be the number 27. I'm like, yes. I will only be the number 28. I was like, oh no, this is okay. You see, so if I keep adding the only number, I may find myself with 75
But then I don't
students.
get any tutoring.
I will end up finding myself with 75 students in that class.
So where am I going to get my tutoring?
See, he can help you.
Okay, so come in your office every day.
Yes, yes. Yes, I'm going. You want to